Hello guys, it's the Caribbean Bookworm, and in this video I wanted to make something a little bit concise, short, hopefully, since I've been making these journey to relativity videos which are very lengthy, and there are still two to come that I have to edit, but it just takes a long time. And I wanted to in essence talk about, say, if I were to talk with my younger self, someone who's very curious about learning physics but doesn't exactly have a little bit of a railroad and paved way to go, how basically I would tell him to go about it. And this really made me think because, for example, I have some comments in some of my recent videos asking me about like which books to get for certain subjects or something. And also I recall having a conversation and a while back with a very interesting guy, a music teacher that I had. Unfortunately, he passed away, but I remember he was, even though he was into the arts, and he was of a very senior age, he was very curious about learning astronomy and physics, and he wanted to ask me like how he should go about it. And right now, having gone a little bit through at least my first year of university in the field, I have a little bit more of a stronger, concise manner which I would suggest people going about this. Of course, that doesn't mean that the things of which I recommend are necessarily the way you have to go. If you have a different way in which you think might be a bit more fruitful for your case, go at it, go ahead, jump into it. As a matter of fact, I think the thing you should take out of this video first and foremost is that if you want to learn something, don't let basically traditional pathways and traditional basically setups and ways of going through something define what you're learning. You can learn very advanced stuff on your own given the dedication, time, and interest, of course. So with that out of the way, let's jump into it. So as I said before, I'm making this video coming out of the perspective that I'm talking with you. I'm talking with someone who's very interested about physics but doesn't know exactly which way to go about things. And with that, I have to keep several things in mind. I have to keep in mind that, for example, your high school education might not be the same as that of the other person watching this video. So we can have different backgrounds right here. Some people might have had a little bit of mathematics already. Some people might not have had a little bit of mathematics. Some people might have had mathematics, but a long time ago. So rest assured, I'm keeping all of this in mind as I'm giving you my tips. So let's actually, without further ado, actually jump into things. My first tip would actually be a very innocent tip, but it's a very crucial one for motivation. And that is read some popular science books. It's, in my opinion, the most fun tip I can give you out of all of these is basically start reading some pop sci physics books. Read books like that of Hyperspace by Michio Kaku, even though I haven't read it. I heard it's a really fun book. Read stuff by Brian Greene, like The Hidden Reality, Fabric of the Cosmos, The Elegant Universe. Read, especially in my opinion, a good pop science book to go into is 6 Easy Pieces by Richard Feynman. Despite the man's personal problems and things which dramas that happened with Feynman, I still think he's a really good explainer, and I think a lot of people think that way because he was able to make one of the hardest concepts in physics very intuitively clear to scientists. So I'd highly suggest you delve into 6 Easy Pieces. It's basically taken off of a set of guest lectures which he gave to I think University of California, to a bunch of undergraduate students on different topics. And in 6 Easy Pieces, he goes condensedly into they summarize some of these things which he talked about, like conservation of energy, some of the basic ideas behind laws of physics, some of the laws of gravitation, Kepler's laws, which I think was my personal favorite, like him explaining Kepler's laws. That was really mind-blowing. And I know for some people, the last chapter in that book about quantum mechanics is the mind-blowing bit, which for me, it was very elegantly and interestingly explained as well. I personally like gravitation a little bit more than quantum though, so the Kepler's chapter is what did it for me. So it's a really good book. Case in point, look into popular science books. Go on websites like Goodreads and look up these various basically popular science physics books and astronomy books. Notice that I haven't mentioned astronomy. You can look into books by Carl Sagan, like Comet by Carl Sagan is one which I personally really want to read. It's like he's describing basically things out of the point of view from a comet that is basically going throughout our solar system and describing everything that is passing by, like the planets, the asteroid belt, belt, etc., etc. Of course, there's the magnum opus Cosmos by Carl Sagan, in which he goes basically into a lot of astronomy and a lot of other sciences as well, as general as he can. There are more astronomy book recommendations, which I will try to place here, here, and here, maybe. Like, I don't know how many I'm going to manage to fit into this video. For astronomy, I think at least there are a lot of good popular science book out there, because people in general, even though maybe they don't want to become scientists, people in general are interested about space. And why wouldn't they be? Space is very freaking cool. There's a lot to talk about it. So yeah. So that's tip number one. Tip number two is, once you get a little bit of the pop science going, once you're really curious about physics, you might not understand everything that some of those people have written, but you are at least a little bit used to the jargon, used to a little bit of the way in which scientists have discovered things. Now you can properly, in my opinion, jump into at least what I think is the most important thing in terms of formally learning physics, and that is jump into mathematics. There is no way to dance around this, but you really do need mathematics if you want to at least very seriously learn physics. So jump into some elementary algebra, some basic pre-calculus, and things basically which will set you up for learning calculus. And that sounds very wish-washy, but I even have very tangible basically ways of going about this. One way is through the internet, and that is using the website of Khan Academy. Khan Academy is a brilliant source in which you can learn even when you go through on the website and you go into mathematics, if I'm not mistaken, or math. You look at the various elementary things which you can learn, like algebra 1, I think, and algebra 2. There's geometry as well. Basically, try your best to learn these topics. And on Khan Academy, at the end of, I think, every module, there's like a quick quiz you can do. You can take those quizzes and basically just refine your basic mathematics knowledge in order to jump into, I think they have this on Khan Academy as well, in order to jump into pre-calculus and then onto higher level stuff. There's even a book which I'd highly recommend, and I mentioned this before in my video called like How to Get Better at Mathematics, and that is the book Basic Mathematics by Sergi Lang. Only this time, I even took the liberty to show you guys which chapters I think are relevant and why. I'd highly recommend from part 1, so the algebra bit, all of the 4 chapters basically. So chapter 1, 2, 3, and 4. The numbers bit, talking about fractions and some basic rules of addition and multiplication and such. Pretty handy stuff. Do some of the exercises, by the way. Don't only read these books, like actually go through the exercises when it comes to like learning material. You can, if you want, you can go on to the interlude on logic and mathematical expressions. Not really necessary though. It's more so if you're more interested in pure mathematics, if you're interested in the language of proof and logic, then you might want to read that for your own curiosity. But general though, not needed in my opinion. So you can just move on to part 2. And part 2 about intuitive geometry, I'd highly recommend chapters 5 and 7. Chapter 7 very sneakily introduces an idea that will come back in calculus, and that is the idea of the integral. Won't talk about too much. Don't talk too much about what that is. But if you read chapter 7, and if later down the road you do calculus, you'll get what I mean. Chapter 5 is pretty handy, and it ties into the part 3 of this book on coordinate geometry. I'd highly recommend chapters 8 for the same reason which I'm recommending chapter 5 of part 2, and that is that it actually delves a lot into the foundations of Euclidean geometry, and that is the geometry of flat space. So knowing, for example, things of properties of triangles, knowing properties of straight lines and line segments, all of that good stuff. Really important for later on in physics. For part 3, I'd further recommend chapter 10 and chapter 11, especially chapter 11 because trigonometry is just everywhere. And in part 4, on the miscellaneous bit, I'd recommend mainly chapter 13 on functions and chapter 15 on complex numbers. Of course, there are other chapters in which you can go through, and there's even the book ends on matrices, which is a very crucial thing in like further math. But I would actually put off learning matrices from this book because it jumps immediately into showing that matrices are like arrays of numbers. And I don't think that is the best way, in my personal opinion, to learn about it. You might, of course, disagree. In my opinion, it is better to learn about matrices in terms of this thing which does something, for example, to a vector, like it's an operator basically, as I think that version of it is very intuitive for further physics concepts. But yeah, so for that last bit, just the chapter, just those two chapters that I mentioned, more than suffice. Furthermore, besides the basic mathematics book, I have another book recommendation, and that is this, well, can't really censor it, but it's the No BS book to math and physics, or the No BS Guide to Math and Physics by Ivan Savov. And this is a really nice book. I used this book, for example, to learn about integrals, I think 2 years before I formally learned it at school. And it's a testament to this book. It's really good. It explains a lot of calculus, actually, in a very elegant and concise manner, and it uses less mathematical, like he doesn't stress too much about mathematical rigorness of thing. But for this one, I won't give a step-by-step look of the chapters because I think every chapter in this book is pretty much handy. Though I will say that if you get this book, in the first chapter at least, where he just talks about basic preliminaries which you need before moving on to some basic ideas in calculus, there is a bit on ellipses and hyperbolas, which I don't think are crucial to get the hang. They're not really fundamental and essential to get the hang of, at least from what I am aware of so far. So I wouldn't stress too much about getting those down, like these conic shapes and things like that. But nevertheless, it's an interesting read if you do have the time and curiosity. But in general, the No BS Guide to Math and Physics, pretty handy if basically you went through the topics on the level of Khan Academy out to pre-calculus, or of the basic mathematics book which I just showed you. So if you have that down, my step 2 or tip number 2 was to basically get some basic mathematics up to the level of pre-calculus under your belt. If you have that down, my tip number 3 would be to delve into some introductory physics. So introductory physics would be, again, depending on which country you come from, high school level physics. Very different, but I would say look into A-level physics or AP level physics, as you can see it online. And there are some really nice channels explaining this topic as well. Like there's I think Dr. Physics A, if I'm not mistaken. He writes with his markers and such. He's really good at explaining A-level physics, and he even explains some really high concepts in physics. But for A-level stuff specifically, it's a really good channel about explaining stuff. And I'd highly recommend it. The only thing is you'd want to practice as well, because just learning this stuff isn't, or just reading about and looking at this stuff isn't sufficient. You want to actually make some problems in order to actually be somewhat proficient, and for that I recommend either using Khan Academy, again, since they do, I'm pretty sure they do have AP physics or A-level physics. And if not that, there is a book which I don't personally have, at least not physically. I have it digitally. It's called the Shams Outlines book for practice problems in terms of A-level physics. And it's a pretty good book. The Shams Outlines book, they're filled with exercises, and I'm pretty sure out there exists a solution manual to them. So they're pretty good books just for practicing alone. So if it comes to, for example, pre-calculus or A-level physics or some of the other topics which I'm going to mention, Shams Outlines, pretty good for practice. So that's my tip number 3, basically, to jump into A-level physics or introductory physics. And not because it's crucial as a stepping block to higher level stuff, because in essence you can get to higher level physics without even having done A-level stuff. But it's more so to get used to some of the topics that are going to come up in those advanced level physics, so that you're not wrestling with the physics at the same time as with the math. So with that as our tip number 3, let's jump into our tip number 4, if I'm not mistaken, or I'll just say the next tip so that I don't confuse the numbers. But my next tip would be to actually now jump into some actual higher university slash college level mathematics. So if you have done, for example, in tip number 2, your basic math and your pre-calculus. Like tip number 2 was basically to get your math up to pre-calculus level. If you've done that, now you can jump, in my opinion, into the two very crucial like subjects for any further higher level physics. And that's also whether or not you want to jump into a little bit more of the theory in physics or a little bit more of the practical side of physics, because that also matters, but that's little details aside. If you want to jump furthermore into physics, then you would have to do single variable calculus or just calculus and linear algebra. And calculus ties very nicely into the pre-calculus material that you learned. So in essence, for example, if you use the No BS Guide to Math and Physics, you've learned quite a bit of the essential concepts in calculus already. But furthermore, in this tip, I'm mentioning it again since I want you to basically hammer down on that, like practice that more and more, and maybe even use a formal university like textbook like Adams and Essex calculus or Thomas calculus. Basically, for calculus, you want to jump into limits, so jump into the different techniques of limits, L'Hopital's rule, and these different exceptions you could say when taking the limits of things. And then you want to jump into, of course, differentiation. You want to jump into integration, these various integration techniques, and also you want to jump into sequences and series. So with sequences, looking at things whether or not they converge or diverge, the ratio test, looking at, for example, things like Taylor series and Maclaurin series and these various expansions. They're pretty useful. They're very much standard things you get in calculus, or if you're in the US, they separate these into Calc 1 and Calc 2. But in general, I will just call them single variable calculus, since that's what it is. It just looks at functions which depends on one variable and the calculus of that, basically. And if you have that down, calculus comes in pretty handy for a lot, if not almost every physics branch out there. But furthermore, a branch that is equally, if not in my opinion, even more important than calculus, that would be linear algebra. For linear algebra, the prerequisites which you need are very hand wavy. And I'd say if you have just basic algebra under your belt, so if you, for example, did algebra on Khan Academy or from the basic mathematics book, I think you're already good to go to jump into linear algebra if you wanted to. But of course, depends on your own pace and time. Linear algebra basically looks at these various abstract concepts of vector spaces and linear transformations, and it looks very much, in essence, more closely at things which have a linear relation with each other. And it's a very powerful tool. For example, you might have seen in physics a lot of times that forces are drawn as vectors. Well, if you have a vector, so say a force vector, and you want to maybe make it a little bit larger or squeeze it or orient it differently in terms of space, then a very powerful way in which you can do this is by applying a linear transformation onto your like object, your vector in this case, and the thing which applies that linear transformation is something called a matrix. And the matrix is the thing which you might have seen that looks like a bracket with a bunch of numbers written as like an array of numbers, you could say. And this whole idea is the essence of linear algebra. Speaking of that, the resources I would recommend for calculus, I will recommend some for calculus and linear algebra separately. It's in terms of textbook, my personal favorite for calculus is Thomas Calculus. But in terms of YouTube videos, there is a YouTube channel out there that looks a lot like Khan Academy, but it isn't Khan Academy. It's something, I think, the organic chemistry tutor or something along those lines. And it's a pretty good YouTube channel, especially for calculus. So I'd highly suggest that. It's what got me through my calc course, that and Thomas Calculus. And besides that, there's also Patrick GMT, which makes some really nice videos, especially on limits in regards to calculus. So I highly suggest that as well. And for linear algebra, there is, of course, visually speaking, there is no better, in my opinion, channel than 3 Blue 1 Brown. Like his playlist on the essence of linear algebra. It's gorgeous stuff, but I'd recommend you use that in supplement to a formal textbook on linear algebra and some formal videos on linear algebra. So for some of the more formal videos, like on the category of Khan Academy, Organic Chemistry Tutor, or Patrick GMT, I recommend you can check out those as well. By the way, I'm pretty sure they have linear algebra videos, but the one which I highly recommend is the one which I don't remember his name, but I will put like an image of him and his like one of his thumbnails or and YouTube video and his channel name. That is the channel which I highly recommend you check for linear algebra. His playlist is pretty good, pretty straightforward. He goes through some exercises as well, so or some examples basically, and it's pretty good for learning linear algebra for the first time basically. And in supplement to that, if you want like visual like imagining of what is happening, then there is no better like source than 3 Blue 1 Brown. His animations are like the stuff of dreams. Like it makes linear algebra make so much sense and make it so much more powerful and beautiful as well. Those are basically my tips for in terms of, well, the higher level math courses. There is of course more, but that becomes really specific. And lastly, in my last tip, basically tip number 5, is now you can actually jump into some higher level like physics courses, and it depends on what you're curious about. Some people will tell you to go the traditional, like if you're self-teaching, by the way, this is all if you're self-teaching. If you're going to university, you might have a more specific outline already, but if you're self-teaching, some people might tell you to, oh, do it the traditional way, like jump into classical mechanics and then jump into things like thermodynamics and then jump into electricity and magnetism and then perhaps higher level electromagnetism, etc., etc. But one thing I noticed is that if you wanted to, you don't really have to do this. You can learn things after having like calculus and linear algebra under your belt. You can practically almost do whatever you want. Almost. I'd still say, in my personal opinion, that one higher level physics course, which I still suggest you go into, is classical mechanics, and it might seem tedious and boring as to why, but that course, like that subject, even though at times painfully hard, it in essence forces you to think like I'm noticing to think in terms of like physics. Like it forces you to think of problems in terms of physics and tackle things in a very different manner than you used to, because up to this point basically you've read some pop science books on physics and you've done a heck ton of mathematics, but physics is not necessarily mathematics. Physics, in my opinion, is slightly harder than math. Like the math itself, that which a lot of people think is going to be the hard bit, and notice in my opinion, and in a lot of people's cases as well, that the math is actually not the difficult bit. The physics is. And I can even give you a solid example as to why. And you will notice this if you, for example, dive into classical mechanics. The reason why mainly is when you're learning the concepts, it's all fine and dandy, and you're creating these connections and dots in between different concepts together. But when tackling a problem, something as deceptive as a pendulum, like hanging and going to swing basically, can be turned into this ridiculously complex problem. And that is, in essence, one of the main gist as to why the physics is actually much harder, because you have to set up your problem from scratch. You have to basically take your problem, take a scenario, and from that scenario, you have to basically decompose and kind of look at what factors are playing a role, how I can, in essence, basically define my initial conditions, you could say, in terms of physics. So you're defining your initial condition in terms of what is the initial velocity, what is the initial position, what is this, what is that. You have your basically information, and from that, you're going to think, oh, how can I basically tackle this like very pragmatically and practically. In tip number 3, I mentioned that you can delve into some intro physics. In intro physics, you can get away with, for example, memorizing some equations and just throwing equations that work. On higher level physics courses, you can still do that, but it's going to be very inconvenient. You're going to want to be a little more concise with your energy and effort. That is at least if you're making tests. If not, there is no rush, but I still try to remove the habit of finding an equation to throw somewhere and actually think as to what is happening. So there's a bunch of videos on like tips of solving problems in terms of physics, and it becomes a thing. But I think there is no better lesson than just diving into it yourself. And I think, and this is the reason why I'm recommending classical mechanics for you to jump into your first formal like physics high level concept. Classical mechanics is the perfect place to do this, like to think in terms of problem solving, how you solve problems in physics, some other ways of thinking which are very beneficial for higher level physics. And for that, I have no better recommendation than Classical Mechanics, the Taylor book. There are more physics books out there, like Crackery. Crackery is also very one at least that I was supposed to use. Crackery's Classical Mechanics, also pretty fine. It's good, but I just very much like Taylor a lot. So I'd highly suggest using Taylor for classical mechanics, and it's pretty nice. You even have like a lot of integrals written right here, and I think even like spherical coordinate stuff like somewhere in the back right here. So Taylor's book, pretty nice, and by the end it even jumps into some like supplementary stuff like the theory of relativity and like the wave equation and stuff like that. But that is not the only reason why I'm recommending you to start with classical mechanics. There are two more reasons for that. One is which you're going to notice how important something known as differential equations are in physics. And I know when I was in high school, at least I had no freaking clue as to what differential equations were, because I saw the word differential and I just thought, oh, you just have to differentiate a bunch of stuff, right? But differential equations are not essentially just that. It is indeed an equation filled with these various derivatives. So you might have y double prime plus 2y prime plus 3 is equal to perhaps a constant in the case of a non-homogeneous second order differential equation. But in essence, the main gist about differential equation is you're solving for, when I say, for example, y double prime and such, the second derivative of a y function, you're solving for y. So in essence, what you're going to get is not a value of, for example, solving a quadratic equation, you get x equals plus minus this, that. You're getting y of t, for example, is equal to something, something, something. So you're getting a function as your solution rather than a actual finite value. So this is the main difference, and this is why differential equation on its own is a whole course in it of itself. So diving into classical mechanics will probably force you to learn some of this, but it's all right because you've done calculus before and linear algebra, and in essence, especially calculus, single variable calculus, is all you need to start learning differential equations. So in essence, if you're learning classical mechanics and you bump into something which you don't know how to solve, like you don't know if you have to integrate something like 2 times or something in order to solve it, or if you try integrating stuff and that doesn't work, then you know that, oh, I might want to look into differential equations and see how to solve it, and you just learn how to solve it. Basically, you don't have to do the whole field and subject of differential equation, but it introduces you to it in a very nice way. Also, the second reason why I say that classical mechanics is a good starting point in terms of higher level like physics course, because it introduces the concepts of the Lagrangian and the Hamiltonian, and these are very powerful things because in essence you can work with any set of information that you want, so you don't necessarily have to look at things in terms of oh, I have my position vector right here that is dependent on time, and if I take the derivative of this, I get my velocity, basically my velocity vector, and if I take the derivative of that, the acceleration vector that depends on time. You can have basically things that depend on other inputs as well, on say angle and whatever else you want to use, and you can still get away with solving your problems. And in essence, it even makes some basically classical mechanics problems much easier to work with. For example, instead of using a lot of force diagrams in order to solve a problem that has to do with forces and such, you can more powerfully and abstractly solve your problem by just knowing the energies of that system. So knowing, for example, its potential and its kinetic energy, you can know pretty much everything about your system. So it's a very powerful tool, and it comes up even in modern physics, so things that are of higher concept. And it's the main reason why I think you should learn classical mechanics. Unfortunately, even in the course of which I had, like, they didn't talk too much about Hamiltonians and Lagrangians, but I think it is the most important bit of that course. So highly suggest you do classical mechanics for that bit. So once you do that, right now you're pretty much, even if you're not in university, you're pretty much a full-fledged physics student. Basically, you're thinking in terms of a physics student, at least in terms of like your math and physics courses. So right now, basically what you do with your time is just it's dependent on what you want to do. So for example, if you want to continue learning like things like electromagnetism, you go right ahead. If you want to learn for math's sake things like multivariable calculus, or dive a little bit more into that which I mentioned, like differential equation, you can do that as well. If you want to learn a little bit more about basic astronomy, you can do that. But if there's one thing in which I will mention right here is if you're thinking about, while pursuing physics professionally, I'd suggest you start thinking about various fields in physics and not just the ones that you're constantly hearing about. So this tip only applies if you're actually serious about going to university, or if you're already in university and you want to basically get a little bit of a step ahead in terms of knowing what you might want to do, basically in terms of like research and such. So the manner in which you can do this is by not allowing your curriculum to limit your choice of learning material. So for example, if you're interested in climate physics, if you're interested in stuff like meteorology, climatology, and climate models and such, remote sensing and such, then I'd suggest just look up resources online, like on insert, like for example, meteorology undergraduate textbook, and after that, Stack Exchange or Reddit. Stack Exchange is particularly really good, but you can try Reddit as well. Reddit sometimes has some surprisingly insightful information, but you can use online resources basically to learn stuff by yourself. Like if you want to learn, for example, geophysics, or if you want to learn biophysics, which is an interesting field in and of itself, or if you want to learn some of the general physics courses, like say your university doesn't have a proper statistical mechanics course or a proper relativity course, then you can still teach yourself these things by looking up resources online and just, well, basically self-teaching yourself. And you can either jump into the material right away, or you can just look up the prerequisites which are needed to learn, for example, the theory of relativity. Yeah, if you jump into it right away, it's pretty nice. You're already busy with what you're interested in about, and if you notice that there's something that you lack the knowledge of, you can always go back and kind of refresh. But it's a nice way of going about things. And for this, for example, in terms of general courses, if you want a nice little like set of books which might help, is there are these series of books called The Theoretical Minimum by Leonard Susskind, and they're really nice books. You can read them even at the popular science book stage, basically. At he writes very concisely and very informally, and he has a really good book on quantum mechanics. I'm currently going through it myself, like piece by piece, and it's Quantum Mechanics: The Theoretical Minimum by Leonard Susskind. Has a really beautiful cover. All of these look like this, but of course the equations for them are relevant to the field. Like this one has like quantum mechanics stuff written on it. But it's a really good book. If you learn linear algebra, you can already read that book, which I've just shown, because it's just basically flat out. In regards to mathematics, quantum is flat out linear algebra. But he has books like that for classical mechanics as well, which maybe you might want to use to supplement your learning of classical mechanics. And he has one on special theory of relativity as well. It's a book on the theory of relativity and classical field theory, which is basically just Maxwell's equations and electromagnetism, or at least a branch of it is that. And this year, from what I've seen, I think on Goodreads or Amazon, is that he might be publishing one on the general theory of relativity, which is pretty cool. So those are a way to go about things if you want to learn further subjects. Like for example, say you've done classical mechanics and you want to learn quantum, then you can try the Theoretical Minimum book of Leonard Susskind. But I am saying this as a general and final tip because a lot of times you might limit the scope of what you want to do to the courses that are being offered at like your specific institution, and that doesn't necessarily have to be the case. You can literally, if you want to teach yourself something, you can literally find sources everywhere online, like MIT Open Courseware, you name it. There are videos for so many things. So if you want to learn any other branch of physics, and there's a bunch of them, like some of the ones that I mentioned before, then you can most definitely still learn them. So, yeah, I hope this video was informative. It turned out to be somewhat longer than I anticipated to, unfortunately, but at least it's not like an hour long, so that's pretty nice. I hope you find this useful. This is meant literally for like the general person wanting to learn physics, so I really, really do hope that you found this to be quite useful, and let me know your feedback and further recommendations in terms of book general interesting stuff. Stay tuned for more videos, and bye.